Hey everyone, welcome again to chemistry. Today we're going to be starting the gas laws. And one of the first gas laws that you learn is called Boyles' law, which we're going to talk a lot about today. So when dealing with gases, the main variables that chemists study to look at gases are pressure, volume, and typically temperature. Okay? There's a few gas laws out there that discuss molecules and moles of a gas. But today we're primarily going to focus on two things: pressure and volume, and how they respond to each other under constant temperatures. Okay? So Boyle's law, just to give you a little background, here's what it is by definition. It relates how the volume, V, okay, of a gas responds to a change in pressure, P. But the temperature stays constant. Okay, so how does the pressure and volume change with a constant temperature? All right. So to show you a very quick example here, we have two situations, right? One situation A and one situation B. And basically in purple, these represent gas molecules. Okay, so purple, let me grab my marker. All right. So the purple sphere, this is a gas molecule. Right. So what are these gas molecules doing? They're traveling at extremely high speeds. And the arrows here indicate their erratic molecular motion, right? Called the KMT, the kinetic molecular theory. Right? So these gas particles are bouncing off the walls of this cylinder. It's a piston that I can compress. Okay? And change the volume of this cylinder. So just imagine, I can, almost like a plunger. Okay, we can change the volume of the cylinder. So this first situation A, it has a very high volume. There's a lot of space for these molecules to bounce around. But they have a very low pressure. Right? If I take the same situation and I begin to plunge down, I begin to compress, and force these gas molecules down, I get situation B. Same amount of gas particles, but now there's less volume for them to move around. And there's a higher pressure. The frequency at which these gas molecules now hit each other and the walls of their container increases. It accelerates because there's less volume. You've experienced this if you go from, let's say, a very vacant subway car in Boston, for example, on the T, and let's say the Red Sox are in town, and the green line is packed beyond its capacity, and it's a tight squeeze. You're rubbing shoulder to shoulder with people, elbow to elbow. That's a very high pressure situation. Okay? So there's a change in the volume and the pressure as the temperature is held constant. Okay? All right. So let's define pressure and volume if we're talking about Boyle's law. Right? So the pressure is how much force is applied to a unit area. Okay? At this time of year right now, we just had one of the snowiest winters on record. The snow in front of my house is about 3.5 to 4 feet high. If I were wearing stilts, not that I would do that, but if I were wearing stilts and I tried to walk across the snow in my front yard, I have all my weight on a small surface area at the bottom of the stilt. That's a lot of force. I'm going to pierce that snow. Okay? But if I take the same amount of area and I expand it and I make a snowshoe, and I spread my mass over a greater area, over a really large snowshoe, I'm not applying as much pressure per square inch. And I could walk right over, right, that snow in my front yard. It's the principle behind snowshoes and how they work. Right? So another form of pressure is a unit that we use is called ATMs, which stands for atmospheres. Okay? So I have my little person here. This is Molly. All right, hi Molly. There she is. Okay. and Molly has all of the air above Molly's shoulders, the column of air in our atmosphere, exerts a pressure on Molly that's equivalent to 1 atm. Now, does that pressure change day to day? Of course. But roughly, we're pretty close to 1 atmosphere on Earth, which is equivalent to roughly 14.7, 15 pounds of force per square inch. Think about that. Every inch of your body has roughly 15 pounds of air pressure pushing on it, right, causing a pressure. In volume, which we covered in the first unit where we covered density, how much space does something occupy? Right? How much space does an object occupy? In this case, gas. How much space does that occupy in liters? All right. So looking at Boyles' law. Don't fall on me. All right, there we go. All right. P1 times V1 equals P2 times V2. All right. So P1 and V1, that's my pressure and volume under the first set of conditions. In some textbooks, they'll call this initial conditions. What is the pressure and volume starting off in this problem? Okay. And my P2 and V2, these are my final conditions. So basically with these problems, you're going to be given you're going to be solving for one of these 3 variables. Okay? As pressure increases, volume decreases for Boyle's law. In other words, this is an inverse relationship, right? It's opposite. One goes down, the other goes up, and vice versa. It's a seesaw. Okay. So let's take a look at one problem. If the pressure of a fixed amount of gas doubles at constant temperature, so my temperature is not changing here, what happens to its volume? Well, let's think about this for a second. If the pressure of a fixed amount of gas doubles, so the pressure increases, my pressure is increasing, what happens to the volume? Well, we just said in the previous slide that they're inverse. So if pressure is going up, volume should be going down. Should be. Well, let's take a look at this. Let's fill in some numbers here. So just to make the numbers work, use some simple numbers. Let's say I have a pressure. My first pressure, let's say it's 1 atm. I'm making these numbers up. And let's say that volume of gas occupies 1 liter. Okay. If the pressure doubles, from 1 to 2 atm, the question asks, what's going to happen to the volume here? What's going to happen to the volume? Let's think about this. So this is doubling, right? So there's a constant. If the pressure doubles, then the volume should do the inverse. It should half itself. Let's figure this out algebraically. Okay? If we're solving for V2, go back to my previous slide, we're solving for the volume. Okay? We're solving for V2. So that means we have to divide both sides by P2. So P2 cancels. So my volume is going to equal my first pressure times my first volume divided by my second pressure. Okay, algebraically. So let's take a look at this. Let's make up the numbers here. So my V2 is equal to my P1 times V1 over P2. Okay, let's solve for V2. Pressure 1 is 1 atm. Volume 1 is 1 liter divided by our second pressure, which is 2 atm. Just to show you how this works, atms will cancel. I get 1 times 1 is 1 divided by 2. Our new volume is half, which makes sense. Right? If our pressure is going up, our volume should be going down. And that's Boyles' law. Right? That's Boyles' law. We're going to do some more of these problems in class. As always, hopefully you're watching the videos. That's the intent here. You're taking notes, if need be, replaying the videos just to make sense. It's like a book, right? The first time you read a book, it doesn't make a whole lot of sense the first time through all the time. But if you read it again and again, it sticks. All right. So I'll see you guys and girls next time in class, and good luck on these.